Welcome YouTubers to this video. Today I wanted to make a description about the skeletal metric hollow cube imperial. Skeletal metrics is an idea that came to me a few months back. I've been thinking about it ever since, and I think it's a really potent way to think about objects in 3D space. In order to create the meta space necessary to conceive of an idea. It's really useful to utilize skeletal metrics so that it can organize your thoughts in a specific way. So today I wanted to explain to you and describe how this skeletal metric hollow cube can be utilized to help you think about the space of an idea and the space of objects. Because when you want to describe an object, there are many ways to describe it, and most people right now use a two-dimensional perspective to try and describe it. They try to use words to fill in the gaps, but it seems to me like it's not precise enough, and it's not filled with content in a sense, or it's not filled with a more complex structure that allows to express in more detail what the form is. So for example, if I'm thinking about an apple does not have, well, it has a set or a defined volume, but the shape of the apple is irregular. And so to understand the form of an apple, it is not an easy thing to do, and there's much complexity in understanding the shapes of the cavities. So for example, in this hollow cube you can see on my screen right now, if there was an apple in the center of this cube, you could see that the cube is not entirely filled with the apple, but there would be gaps at precise parts that would correspond to the shape of the apple, an irregular organic shape that is very difficult to describe accurately. Even with numbers, you can have maybe the weight, maybe you can have the volume of the apple, but it does not describe the shape and the cavities of the torus-like structure of an apple. And all these ideas seem to disappear in favor of simplistic measurements. So that's one of the initial thoughts I had about creating the system, as to how do you understand, how do you express the complex organic shapes, like an apple, different types of fruits or trees, for example, like the density of leaves in a given space. For trees and other things like that, you have to divide space in a different way in order to be able to articulate it in your mind. If you have just a picture of a tree and you have different leaves on this tree, you don't have much information about the spacing of the leaves according to one another. Like how far is this first leaf how close to me is the first leaf as compared to how far is the furthest leaf away from me on that same tree. When you have just a two-dimensional picture, you cannot assess of that. But when you think about it in three-dimensional space, then you can have a better understanding of the relative positions of objects. So that's going to be the introduction to this video. Now let's carry on to more practical applications of this system. So first off, I just want to describe what I have here in this. So I've already made the 3 different videos about this skeletal metric. This is the third one. I made 3, but the third one is about the Windows programming system, which I have in mind. This file here is just the first 2 videos about my skeletal metric playlist. So that's what I wanted to express and explain today. So you can see here that the first cube that I have here has a dimension expressed here. I chose this types of symbol, this bar here, to separate the different dimensions. So the first one is going to be the width of it, so you can read it like a line of a text. The second one is going to be the depth, so you can see that the first plane is expressed in two-dimensional fashion, and then the third digit is the height of this object. Now this is a cube, and I wanted to make it as a cube for a precise reason, is because in the first part of this skeletal metric series I wanted to express the use of grids. Cubes are better to creating grids because they're more regular, so they allow for some simplicity when it comes to these grids. So the grids is like this one over here. So this is just an organization of this cube in space, in different series and rows, and they have different copy patterns. So this is one of the copy pattern that is possible. And you can see here that the interesting aspect of this geometry is when I move around with my view, there are different focus points where the angles of different parts of the cube seem to merge and create these very intricate displays of geometry. You can see all the angles here, they change and they morph and then they align and they create all these synchronicities that are very unique to this type of thinking. Just before I carry on here with the other grids that you can see in the background over here, which are just other types of patterns for the copy for these grids, I do want to just express here why this cube is expressed in the way that it is. So if I take this cube here that has a dimension of 1 feet by 1 feet by 1 feet, I can derive the location of the center by simply getting half of this dimension on every axis. So that means that the center here is at 6 inches, 6 inches, and 6 inches. Then you can find the center of the cube. Now, this is very important, and it makes a big difference between other types of measuring system or metaphysical thought patterns, is because I want to use this cube in order to identify the center of the cube. And that's one of the pivotal aspects of this system. Where is the center of the cube? So if I'm to put an apple in this cube, I can orient the apple and position the apple according to the center of the cube, and that's the important part. The reason why that is important is for many different reasons. But simply put, it allows me to understand space in an easier fashion. So for example, if I'm looking at a picture of a tree or a forest, I can say, well, the average tree has a dimension of, let's say, 1 feet in diameter. That would be the average tree in this forest. But then if I take a picture and I get this conventional measure of the average tree size, then I can utilize the dimension of that and apply it to trees in the distance and measure the difference in size of the cube in the distance to where I am, and therefore derived how far the tree is, or how far the second tree is as compared to a closer tree. So to understand that, you need to identify the center of the tree, because if you do not have a center of the tree on which you can draw the circle, then you cannot see the difference in distance. You cannot measure two different objects if you do not have an independent center for these two objects. So it's a little bit of a complex idea to express. I'm sure I'm going to find better words to express all of this in a later point, but that's that's what I have in mind for today. So it's important to identify the center of this object, right? Because if I'm thinking about, so here I have the dimension of 1 by 1 by 1, which would be like a section of a tree. It could be the same kind of size as a tree. But what if I want to measure, say, in terms of hand size, say a fist size? Then a fist size would be more like 6 inch by 6 inch by 6 inch, or maybe 3 inch by 3 inch by 3 inch. And I could ask questions like, how many fists are necessary to divide, or how many side-by-side fists would be necessary to bridge the distance between the two ends of my desk? So I can see the distance in my desk and I can measure the amounts of fists necessary to divide the whole space. So things like that require an independent center, because then I can count the amount of fists, or the space necessary for one fist necessary to fill this whole gap. So that's why it's important to identify the center. Now let's put that aside for the moment and carry on with the grids here. So if I want to divide, let's say there is a desk at the bottom of this grid here, and I want to divide the space above my desk in a way so I can have different maybe structures. So maybe on the left side I want to have like a rack with different books, or maybe a bookshelf on the left, or I want to have a computer on the right. Over the computer I want to have another object, let's say a painting, and then in the center I want to have my screen. These are all different ideas. They're different objects, and these objects have a different center to themselves. So let's say I want to have a bookshelf on the left side of this desk, and I'm going to say that at the base of this grid here is a desk. I'm going to draw it here, why not? So let's say this plane here is my desk, and now I want to look at my desk and I want to organize objects in a some kind of a rack or some kind of a shelf-like system. So I want to divide the space so I can place different objects at different locations. But in order for me to place these objects at those different locations, I have to identify a center for these different locations, right? So if I want to have a bookshelf on the left, then the bookshelf has maybe here 1, 2, 3, 4 different centers where I can anchor the bookshelf, right? Or I can put it on the top flight, or I can put it at the bottom row here, or I can put it on the right side. But the idea of this grid is that it gives me different centers in order to anchor my ideas. So I can use maybe one of the cubes to depict a mouse, the other here I can use to depict a keyboard, then the other one in the back here, maybe that would be the screen, and maybe here would be wires. And these are all different ideas, and now they have a grid-like structure in order to catch those ideas and to position them in space according to one another. So that's why it's important to have centers. This system is about identifying the middle of an object and the relative position of this middle according to other objects. So now I use the example of a desk here to give you a semblance of idea that you can use this for, but you can use this to an infinite amount of purpose. So that's why I think it's an important system, because now I used the idea of a desk and different objects on the desk to represent the necessity, to represent the usefulness of this grid system. But you can also utilize a system like this to divide apartment spaces in architectural developments. So if you identify here your basic skeletal metric for the average size of a room, for example, you could choose dimensions in the likes of 20 feet by 40 feet by 20 feet, and that would give you a basic size that you can use as a metaphysical structure, and then you can gather many of these structures together to create a grid, and it will give you an idea of how much space that you need to fit this geometry, right? So if I want to have, let's say, a strip mall with different stores, then I can identify what would be the average the average rental space by a set of dimensions, and then I can stack them up together as just a empty grid that would look like this, like maybe one of these rows, and then from there I can start to draw more detailed representation of these spaces and express more of their details. So it gives me this underlying structure that allows me to think about where other objects can go, because then I can use the cube and I can subdivide its parts to an infinite amount. And so if I define the space of a rental store, then I can divide the parts within the store in smaller cube size, and then smaller and smaller and smaller until I reach a highly detailed environment. But the structure remains the same. I need to have a kind of a web, a grid, to catch the ideas that I want to put in that retail space. So I can use this metaphysical thinking pattern to lay out different ideas and catch them in space, and then I can go back to them and clarify them over time. So this is for the basics of the skeletal metrics. Now I just want to go here into the different complexities of grids. The one here that I thought was best was this one here. So the copy pattern was origin and minus origin. So what that means here is that if I started my cube here on the origin, that's going to be the origin, then the negative origin would be the opposite of that corner here. So if I take this cube and I copy it to the opposite origin, that's what I get. But what I did is I utilized this base grid here. Let's see, that is 4 by 4 by 4, and then I copied it to origin and minus origin, and it created this grid here. Now you can see how intricate these synchronicities, the angular convergence. I'm not sure exactly how to turn this, but you can see how how moving around this cube allows you to focus on certain patterns that happen from just the position of the grid itself. And I think that there's something very interesting in there. So I did try it with a bunch of different patterns to try different ways to organize it. I think this one was a good one too, but this one is a little bit too condensed, I think. But it gives you an idea of how many measurements you can put in a rather small space, right? All of these lines are the expression of this cube, but it shows you how dense like it can really be. So I think that's really interesting. You can see these beautiful motions of line happening in this cube, which I think is fascinating. So I'm guessing that there's a lot of mathematical formula that would explain this convergence of lines, but I did not figure that out yet, so it's going to take some time for all of this to happen. Then what I did is I wanted to express the circular geometry within a cube. So like earlier I was talking about a tree trunk. So you would have to think about a circular geometry in that sense, because a tree trunk is not square. And so how to use circular geometry within a system like this would be in the likes of this. So the dimension of the cube would be used as the dimension of the diameter of the surface, so that the circle would fit within the cube. So that means that by default, if you use circular geometry with this skeletal metric system, that means that there is this space between the corner of the circle, the corner of the cube and the circumference of the circle, and all the space here is empty, right? So you cannot count it as being part of the volume. So what I did here to express this idea with a little bit more detail is this object here, which I do not have a name for yet, but I think it's going to have a name of its own. So what this is the addition of these flat two-dimensional geometry so that they can create a cylindrical shape from one side of the cube to the other, divided into 10 different profiles or slices. And I did this for all 3 axes. So it's like 3 cylinders merging together. Now you can see that the corners of this cube here, this space out here and the bottom here, is negated, so this is negative space, and that's going to be necessary if you want to consider space with skeletal metric in a circular geometric fashion. So you need to take out the these not excess, but these parts only fit for cubic measurements, and in circular geometry all this part has to be erased. Now that's where some of the math has to go to understand what's the size of this, because this is a rather complex mathematical operation to define what space this geometry occupies. This corner shape here with this curve in 3 dimension is a very complicated shape. I am not able today to describe it mathematically, but it does have a mathematical formula. So that's going to be an interesting part of this system to develop. Now, so this is for the basis of skeletal geometry. Now, I also want to bring it to another level here so I can get just a little bit further on why it's useful to use this kind of metaphysical thinking. So let's say I want to design a public park or a public plaza, and I want to create a staircase with wide stairs. So maybe the stair is going to be relatively shallow and it's going to be spread over a large area, but there's going to be small steps. So it's going to be a small incline over a large period, or a large distance, and very wide steps that maybe the steps will stretch from one street to the next or something like this in a small town square. So to think about this idea, I need to define a series of dimensions first. Before I can start choosing what design I like, I need to lay out the space in order for me to understand what I'm trying to draw. So let's say my town square is going to be, let's say, 60 feet by 30 feet. So it's going to be like a small little plaza type thing, a very small thing. Or let's go bigger than that. Let's go 120 feet. Okay. So let's say this is the plaza that I have. This is the area I have to work with, and I want to create a small incline. Sorry. Okay, so then let's say that this place is in an incline, a very small incline of maybe 4 feet over 60 feet. So that's a really shallow angle. So then what I can do is I can decide to divide this line into halves maybe. And then here I could draw steps and say, well, here this is the first step, second step, and then I can go like this, push pull, and I can bring this all the way to here. So then I can have these long stairs that are quite shallow, right? So these very small steps here over a large distance that are very wide. So what I did to do this here is I utilized a two-dimensional thinking system where I drew a plane, and on that plane I simplified my idea into a single line, and then from this two-dimensional plane on which I draw, then I can pull out a three-dimensional shape. So that's 2D to 3D thinking. So that's not utilizing skeletal metrics. All right, and you're going to see the power of skeletal metrics in just a second here. So I'm going to take this area here and I'm going to copy it again, move it left. Now I'm going to use a skeletal metric type thinking instead of this. So you can see how much more detail I can imply in there, or how more intricate the three-dimensional thought is as compared to a two-dimensional analysis. So here, let's say I want to use a shape that's going to be, so my basic skeletal metric shape is going to be 120 feet. Let's say I want to have my steps to be about 8 feet. And then I want to have the depth of the stairs to be, let's say, 3 inches. That's a little bit too shallow. Let's go for 6 inches. All right, so that's gonna be kind of my three-dimensional ruler in some sense. That's what I'm gonna use in order to divide the space on the surface in ways that's gonna allow me to draw it with more detail. So I'm gonna take this here, just make it into a group so I can select it easy. Then I'm gonna erase the faces because I don't need them. I'm going to keep the outside here because this is going to create a little bit more visual contrast. It's going to be easier to see, but these lines are not really necessary. Now the other thing I want to do here is I want to draw the center line to understand where the center is. So my center is right here. So I'm going to draw it from here to there. Here to there. Alright, so now I have my center and that's my object. So then I can take it like this. Whoops. Okay. So then I can take it like this. And now what I'm going to do is I'm going to take this object, and then I'm going to copy paste it like this. I'm going to go x10. So now that's my space. Now I'm using this three-dimensional grid in order for me to anchor other lines. See, so now what I can do is, if I would want to have like a detail, say I want to have some kind of outline for these stairs, maybe some, how do you call this, not detailing, but, shoot, the name escapes me. If I want to have some more details, more outlining and more, let's say I want to have a pedestal on each side of the stairs. Now, if I want to use like the first two-dimensional system and I want to draw a line, there's no place for me to anchor. I'm not exactly sure where. Maybe I can draw a line and put it in a dimension and say I want to have this pedestal be of a width of 4 feet. So I have to type in 4 feet, and I gotta go here, and then how far do I want to go up? Well, it depends. I'm not sure exactly how far I want it to go up. So then I also need to choose another arbitrary dimension. And so it's like I'm trying to draw here. See how this line is just out in the void? There's no place for me to anchor. I can't think about this line according to its environment. I am forced to think up the number and go by the number that I choose. And it's difficult to have a proportional understanding of what I'm trying to draw if I'm just utilizing these random numbers. If I go here, and say, okay, I want to identify a pedestal. Well, let's say then I can utilize this grid here and say, okay, I'm going to have my pedestal be of this height, and then I have my anchor point. Okay, and then I'm going to have it go up to here and go up here and utilize the corner of this grid right here. And then I have the basis for it, so I can just take here and take this pedestal and move it as far as I want. Maybe I want it this big. I can also divide these blocks to have even more detail. If I want to have 1/8 or 1/16 of this size and proportion, I can divide the space, and it's going to give me a bunch of different anchors for me to draw a line on. So then I can take this maybe and do the same on the other side. See, now I have like this allows me to divide the space in a more intelligent way. If I go back to the first one here, I'm just drawing everything out of thin air. I have to have already a preconceived idea of what I'm drawing before I can actually draw it, because there is no grid for me to utilize in order to draw. And that's the difference between skeletal metrics. So you can see here that I utilize different type of shape here to create this grid. Instead of using a cubic shape, I used a rectangular geometry instead, and that allows me to conceive of the space in a divided fashion, so that I can understand what the parts of this object I'm trying to draw are, and I can divide its parts more precisely and therefore utilize its own proportion to draw it better, instead of drawing from thin air or from a very simple two-dimensional plane and always be reliant on external input. You know, I don't have a grid to anchor this first drawing, but here there's many different points I can utilize to draw. Maybe I want to have the pedestal, I want it to be detailed, but I want to have an extra little bit that comes out. So maybe I can go here, utilize another point of this grid out here, and bring this up to here. Maybe I want that to extend to another 4 feet. So then I can go like this, and then I can pull this in. And maybe I wanted that to be just to the center of this one. So now you can see that it's easier. It's easier to latch to anchor ideas when there is this underlying grid underneath it, and that's the whole point of the skeletal metric. I want to find a set of measurements that allows me to divide space in the most effective way possible for me to accelerate my drawing. It's like trying to draw on a blank sheet of paper as opposed to a checkered piece of paper, like in mathematics and these checkered piece of paper. It's if you want to draw something and you have all these lines, it can be a lot easier to draw well than on a blank sheet of paper. And that's exactly the concept I'm trying to push here with this skeletal metrics. Now, I also want to finish this up with the last example. The last one's going to be about trying to draw more of a retail space. So if, let's say, I have a unit that's going to be 30 feet wide by, let's say, 60 feet deep. So that's going to be my shape. Then I'm going to pull this up so I can have a volume. So the volume, wait a second. So the average room is going to be, let's say, at 10 feet high. So that's going to be my retail space. Now maybe in this there's a counter, or maybe there's racks for clothes. So what I can do is I could utilize one of these grids. Like this. So here, maybe I don't need to have these four, so I'll go here and just take one slice like this. I'm going to make a group with it. And then I can utilize this here. And then I'm going to copy it. To 8 feet. I'm going to go x3. Okay, so maybe here, see now I have this grid here, so I can start to pick out the points I think that fit best. If I want to put a rack of clothing or maybe a shelf of shoes or maybe some accessories, then I can say, well, maybe I'm going to use these first 8 boxes here to put on accessories. Then I'm going to use maybe the next 16 boxes here for clothes, and then maybe I'm going to use the rest of them for shoes. But here now, because I have this grid inside of it, it allows me for this second level of detail where I can associate the center of these cubes to objects. And that was not possible before I put these cubes in, because you just have a blank space. There is no anchor point for your ideas. So that could be something. Let's say this is a retail space, so then we have different displays here. Now I can take this and I can utilize it to divide the whole space in order to divide it, but that's not what I'm going to do today. That's not the point. What I wanted to do here was I want to utilize the space of the retail store, or this area here. I'm going to make a group with this. So take this and move this away. Okay, let's say I want to create an industrial development. I want to have 12 units within this industrial development, and so I have to first start with understanding how much space will these 12 units do. So before I can even understand what items are going to be part of the store, I need to first think about, well, how is the space going to be divided within these 12 units to create this one industrial development. So what I can do is I can use a grid with this base measure. So I'm going to take this and erase the surface so I can have just the cube. And then I'm going to find the center of this piece of this room. Okay, so now I have, this is another form of skeletal metrics, right? So I have the center of this room. This is one object, and there is the center. And now I'm going to use this to divide the space. So I'm going to take this, and let's say I want to have 12 units. Maybe I want to have this x10, and maybe I want to use another 2 here, and I'm going to rotate it from the corner here. Maybe I want to have this like that, and then move this here, maybe up to there, and then here, another here. Maybe that's the way I want to, maybe that's how I want my mall to look, or my strip mall. Maybe there's going to be 2 units that's going to be the receiving docks, or maybe there's going to be shipped, and to divide the space. But now it allows you also to look at this and say, is this the best organization for these rooms? Should I organize them differently? Maybe I want to have 6 of them, then a space between them, and then another 6. So let's try that. So let's try 6 of those. I'm going to take this here. Maybe I want this like that. And then I'm going to take this, and I'm going to copy it here. And then let's say I want to have them facing one another and separated by a corridor of about 12 feet. So maybe that's it. Now I can draw a roof over there. That's going to give me just a basic understanding of the skeletal geometry of this development. I mean, this is a very high-pitched roof, but wait a second, I'll just so maybe that's going to be the basis of my structure. Then from this point on, then I can identify other things that I did not think of before. Like, for example, now bathrooms. Where are going to be the bathrooms? Where are going to be the stairs? So then what I can do is I can define the skeletal geometry necessary to express the stair or the bathroom. And then I can take this and then place it at different locations on this grid. So that's going to allow me to divide the space and start to understand where every single part goes, one after the next. And once all the parts are identified with the skeletal geometry, then I can replace the size of this geometry with more realistic ideas. So instead of having the skeletal geometry of a bathroom, I would have the entire bathroom put in place. But the thing is, now that I have identified the center of this room, I can easily place the detailed version of that room on that grid. So it allows you to think about space in a more effective way that is really beneficial when you want to decipher what room should go where and how to play around with ideas. Now, that's what I can do in the computer, but you can also do it in your mind. You can play around with these ideas just for the skeletal shape and the basic geometry that would express the idea, right? So you could you can utilize this system to create just as much as you want of any type of shape that you wish, and it allows you to divide space with a much more precise system than just calling out for numbers. Because if you just call out for numbers, you're going to always gravitate towards the same type of numbers, and it's going to create a mental blockage. It's going to seem like, because there is no grid underneath your ideas, it's going to make it seem more difficult to draw a house. It's going to seem more difficult to organize space, because it's like trying to play checkers without a game board. You don't really know where to put the pieces. Now, it's not because the pieces are difficult to place, but it's because there's no underlying structure if you don't use a system like this. So this is what I wanted to say today. Thank you for watching. I hope you learned something from this. I find it very useful to divide space like this, and I think that there are many different applications for the skeletal metric system, but I have to think about how to express them best to make them work. So I still have some thought to put out for this, but so far I think this is a very concise way to express the benefits of this system. So I hope you enjoyed, you had a good time, and I'll see you guys soon.